Hello, everyone. I'm Monica, and I will be one of your hosts for today. So, today we'll have three spotlight talks in order of World Quantum Week. And before we start, so let's just have a check up on how everyone is doing today. Yeah. So, how are you today on a scale of 1 to 4? So, press 1 if you relate with yung Mona Lisa painting. Press 2 if yung I am chill na cat. Press 3 if yung Happy World Quantum Day. And press 4 if yung excited. So, send your reactions to Zoo. Superposition of 1 and 3 daw, sabi ni Jabez. How about the rest? Send your feelings for today. Ako siguro nasa 3. Happy World Quantum Day. How about the others? 1 to 3, 2, 3. Yeah, 0.5, 1 to 2, 2 and 3 and 4, 3. 1 and 3 and 4. Yan. So, madaming 3. So, let's go. Happy World Quantum Day. Yan. So, for today, our first spotlight talk. So, we'll have our first session na spotlight talk session number 1. And I am pleased to introduce our speaker. So, our first speaker for today is Dr. Gabriel Gallardo. So, he earned a Bachelor of Science degree from the University of Hong Kong, majoring in physics and minoring in computer science. He also pursued a Doctor in Philosophy in Particle Physics at the University of Oxford, focusing on searches for dark matter particles using the ATLAS experiment at CERN. In his early career, he transitioned into quantum computing, starting as a software engineer, and currently he works as a product manager in quantum computing, focusing on designing and building quantum error correction solutions for future fault tolerant quantum computers. Yes. Wow, CERN, sabi ni Jabez. So, yes, our speaker for today used to work at CERN. So, let us welcome Dr. Gabriel Gallardo for his talk.
Thanks, Monica, for the introduction. Could I just confirm how much time do are you giving me for my little chat?
Jabez, can we confirm how much time we have for his talk?
Um, 40 minutes, 45 minutes pa, sir. So we can have some Q&A at the dulo.
Okay, very good. Yeah. Uh, just checking, because if it needs to be shorter, I can shorten it, but if you need something like 2 hours, well, okay, I have a meeting after this, but
True.
but okay, hi everyone, and thanks again, Monica and Javis for the introduction. So let me see. I haven't used Zoom in a while. There we go. Yeah, so welcome to World Quantum Week in the Philippines. And yesterday for World Quantum Day at the office, somebody bought lots of donuts and well, somebody enjoyed them. I didn't enjoy them. I didn't want to get more fat than I already am. But anyway, welcome again to World Quantum Week. Uh, my so let me just a little bit about myself. So I was born in Hong Kong to Filipino parents, and there this is a picture of me when I was something like 12 years old, 13 years old, and I was attending local schools in Hong Kong. So actually, my first language is English because my parents spoke English to me at home. We had a yaya who spoke Tagalog, but I never really picked it up. I can understand um, conversational Tagalog. So like Monica Javis, when you were chatting with me earlier, it's okay. I understand, but I find it very difficult to I don't know to speak it myself. But I also know Cantonese because I had to make friends with all those lovely people there in the background. And if you don't know Cantonese, then well, in this kind of school, you didn't really have any friends. So English, Cantonese, and in secondary school, I started studying physics because I was really interested in how the world works from a very fundamental level. My line of reasoning was the entire world somehow is built on physics, right? You have all of these sort of human kind of sciences like psychology and economics, and really that's just somehow applied biology. And biology is really somehow just applied chemistry, and chemistry somehow is just applied physics, and mathematics is the language that is useful for describing physics. You may disagree with this. Some people enjoy mathematics on their own, but for me, this is kind of how I saw the world. And so I studied physics in secondary school or in high school. And then when I then moved to university, I studied at the University of Hong Kong. So again, I was mostly staying at home, right? I lived at home. I commuted 1.5 hours to the university where I continued to major in physics. But I also took a minor in computer science. So what this meant is that I needed to fulfill something like, I don't know, 20 courses in physics, but maybe 6 courses or 8 courses in computer science. And this I did again because I wanted to. Like I had always loved computers since I was a child. My dad had a Mac. We've always had Macs. And he would always talk to me about programming computers and whatever. And so I was very fascinated by these devices and how they worked. Um, and then I started my research career. So first I was a research assistant at the University of Hong Kong, and then I went for my PhD, or at Oxford they call it a DPhil because they're very particular about the English. PhD is Latin for philosophiae doctorae, uh, but in English it's Doctor of Philosophy. So that's why they're a little bit, particular. But basically, I worked on the Atlas experiment at CERN, and then again, this was out of my love for physics, my desire to understand how the universe works, where it came to be, and I thought if I could study the smallest things in the universe, then I can sort of understand how the world works. And having done that for about 5 years or 6 years, I now know that I know a lot about a little bit. I learned about these particles and how they work, and I worked at CERN, and it was really amazing. But somehow, I came to the very basic learning that you cannot learn particle physics to understand people, for example. You cannot learn particle physics to understand chemistry. Like they're completely different disciplines, but that's fine. I had a really good time. Um, Let me walk you through some of the things that I was looking at when I was at CERN, and then we'll talk about the quantum computing bit. Um, and anyway, all of quantum, this is all somehow quantum. So CERN, you may know, is a research facility that's based in this very beautiful city of Geneva. So this is Geneva in the wintertime. I have seen it in the snow like this. They have a very prominent landmark, this fountain, which goes up to about 200 meters or so. There's a beach here on this little breakwater. Not a nice place to be in the winter, but in the summer, what a lovely place to be. You go swimming, there's a rock climbing wall and everything. And here's me at CERN. So this globe here is sort of a tourist attraction, really. There's a museum on the inside, and sometimes they have film showings. And this picture was taken in 2019, 2018, 2019. Since then, they've redone this place, and it looks a little bit different. It looks a bit better. But people don't work at CERN just to look at a tourist monument, right? They work at CERN because there's cool physics to do. And how do you do the cool physics? Well, as you see this globe here, on the next picture, you'll see it there at CERN. And then, of course, you see the jet that I mentioned earlier. And under the city of Geneva, under the border of Switzerland and France, lies something called the LHC. So the LHC, the Large Hadron Collider. And inside this collider, we can collide protons up to almost the speed of light, and then we bring them to collide with each other. And the idea is that if we give the protons a lot of energy, in this case, kinetic energy, then somehow we can convert all of this kinetic energy into the mass of some particle that may or may not that may exist. And if we can't create it, then maybe it doesn't exist. There's a question in the chat, is CERN the factory of antimatter? Yes, in fact, CERN regularly creates antimatter. Antimatter is regularly created at the LHC. And then there are also dedicated antimatter factories at CERN where we try to measure the properties of antimatter. So antimatter, for those of you who don't know, is just like regular matter. So, there's electrons and then there are anti-electrons, or they're protons and they're antiprotons, or hydrogen and antihydrogen. And the theory is that antimatter differs from normal matter only in the electric charge. So, for example, if you have the electron and the anti-electron, or we call it the positron, um, the only thing that should matter is that the charge of an electron is -1, and then the charge of a positron is +1, but otherwise the mass is the same, and how they interact with all the other particles is the same. And so far, this is what we observe in terms of antimatter. Um, and it forms a crucial part of all the experiments that are performed at the LHC. I'll give you another video just to help you visualize what's going on here. So, or first this picture. So this is what it looks like underground. This is 100 meters underground. There's this giant blue tunnel which curves around. It's about 26 or 27 kilometers long. And the precision is such that sort of small changes in the gravitational field around the LHC can be measured by the LHC, because you imagine if you're trying to send protons around this ring very fast and with very high precision, if the ring sort of expands or contracts or changes shape somehow, this will affect the dynamics of the proton beam that's going around, and you can actually measure this. So you can measure when it's high tide or low tide, when there's a lot of water in the lake, when there's not a lot of water in the lake. This is not what the LHC is built for, but it's a cool thing that you can measure, and it's a cool thing that needs to be accounted for. Another thing is that this machine consumes a lot of power. So whenever you turn it on or turn it off, they always have to telephone the local power companies to just say, hey, we're going to turn it on. Hey, we're going to turn it off. And in fact, early on in the operation of the machine, so in the early 2000s, so 2005, 2008 or so, they would observe that the power going into the machine would occasionally dip for no reason, like just, it would be at some wattage and then it would go down and then it would go up again. And they weren't sure why until they looked at the schedule of the high-speed trains going in and out of Geneva. And they realized that the basically the machine and the high-speed trains, the TGV, were competing for the voltage that was available from the local power companies, and so that would affect the operation of the machine. And now they just account for it. Here's the video that I promised. So here's the LHC again, 27 kilometers in circumference, and you have two opposite proton beams going in opposite directions. You accelerate them to almost the speed of light, and you try to bring them to collision inside one of these big detectors here. So this is one of the detectors. This is called CMS. And I worked on the other detector, which is Atlas. So what this detector is, it's like a giant camera that tries to capture pictures of the collision, or it tries to record the debris of the collision. And from the debris of this collision, we try to reconstruct what happened in the middle, and we try to do some statistical analysis. So this is just a video. It's for illustration. Here's one event that I actually studied. So this event I studied as part of my PhD. We were looking for dark matter, and the idea was that we had a theory. We were trying to follow some theory that an experimentalist came up with to say, sorry, that we tried to test a theory that a theorist came up with that said, okay, maybe dark matter looks like this, and you would observe a collision that looks like this in the experiment. So we studied events that look like this, and so what you're looking at here, this sort of pinkish thing here that goes along the frame is the beamline. So that's the tube where the protons actually collide. Uh, and then in the middle is where they collide, and you can see all the stuff that comes out of it. The most important things out of this picture would be the the two green bars or the two green tracks that spread out, and then the four red tracks that spread out. So what this event is therefore a an event with four muons because the muons are the red ones and we can detect them. We can discriminate what kind of particles are produced. So these are four muons and two jets. So hadronic jets of like either quarks or gluons separated from SAD. So they manifest in a way other quarks and gluons out of the vacuum of the quantum fields and create what are called jets. And you can detect these, and here they're visualized as these green things. So we studied these things. Um, and then and that was my thesis, right? I wrote algorithms that tried to make sense of these kinds of events, and then I participated on three different analyses that were looking for dark matter. So my main analysis was this one, and then I had two smaller analyses on the side, uh, which I also contributed to in some small way. And then after that, I started working here at River Lane. So I wish I had more pictures of me like with other people at River Lane, but we don't take that many pictures in the office. So here's me at the office. And how did I get into quantum computing? I got into quantum computing because at the end of my PhD, I didn't really know what I wanted to do. I knew that I didn't want to stay in particle physics because by that time, my research curiosity had more or less been satisfied, and I wanted to do something else. Um, and then there were also some practical life considerations as well. So I wanted to stay in the UK at the time, and I also knew that, well, to get an academic job in the UK, it doesn't really pay that much. I mean, it pays more than a PhD, about double than a PhD, but it's still compared to other industry jobs that it wasn't that attractive. Moreover, I felt that my field was full of people who were hardworking and passionate, and I felt like personally, I am a hardworking person, but I don't work as hard as the hardest workers, I confess. And if I was neither that hardworking nor that passionate, I knew that, I would not be able to compete even if I had the skills, and my supervisor did think that I had the skills. So I made a choice to leave. I looked for a few jobs and I only applied to a few. I applied to less than 10 after my PhD. Um, and I didn't apply to anything that I wasn't interested in. And eventually, this company took me on, River Lane. So at the time, River Lane was looking for someone who can do both physics and software. And having done my PhD where I did it, and having done the thing that I did, that happened to be me. So I knew physics, I knew software, and so they took me on as a software engineer. And for about 2 years, 2.5 years, I worked for them prototyping various things in C++ and in Python. So we tried various things like if you asked ChatGPT, what does Riverlane do? It will tell you what we did in 2021 and 2022. And by the way, if you ever use ChatGPT to write a cover letter, always check that what it says that the company does is still the thing that the company does. Um, because, the training data is old. And so if you write to a company saying, "Oh, I'm really excited about this product X that you're working on," but actually the company moved away from that product X 3 years ago, it doesn't look that impressive. So remember to do your research and verify, what the output of your chatbots. So anyway, I was working on what ChatGPT thinks Riverlane still does. I was doing some C++ and Python and architecture work and sort of moving up the ranks as a software engineer. But then I got bored. Uh, I didn't want to do the engineering anymore, and I wanted a bit more like understanding of how the company works, how the industry works, and I wanted to be in a more people-facing role. And so the opportunity for me at the time was to do product management. Um, I'll talk about my journey and then I'll talk about what that is. So my journey was that there were mentors in the company who I really appreciated and admired, and I told them, "Hey, I like what you do. You're a product manager. I like what you do. So can I do it too?" And they helped me to learn the skills needed to be a good junior product manager. And then when they left the company, I eventually took their jobs. They didn't leave because of me. They left because they had they wanted to start families elsewhere. But when they left, they left a place for me, and I started to fill it. And now I work at the same company, in River Lane, creating quantum error correction products. So instead of, doing the hands-on engineering of making the products, now I make the decisions about the products. So what to build, um, what features to include, what does the user experience or the user interface look like? What kind of like hardware does our product exist on? How does it connect to other systems inside a quantum computer? How fast does it need to be? What does it need to do, et cetera, et cetera, et cetera. So I make those decisions. I don't make them alone because I need to work with the engineers and the scientists to see what's needed and what's possible. And of course, I work with the business leaders to make sure that this is a viable business thing to do, as in the company is willing to invest the money into some product idea and that there's a likely return on their investment. And then, of course, I talk to the customers who would take this thing on. Because if we make a product and nobody buys it, then that's not really that useful, right? But of course, the dream maybe is to make the iPhone, right? They make the iPhone and then everybody loves it. It changes the world. That is the dream, in fact. Um, something that we all aspire to, and you only get that by actually doing the customer research and being that, and the product manager is sort of the representative of the customer inside the product, representative of the customer inside the company, and advocating for their needs and making sure that they have a good user experience. So that's probably what I do. But anyway, maybe what's more interesting to this crowd is the actual quantum stuff. So we work on something called quantum error correction now, and that is the idea of turning unreliable physical qubits into useful logical qubits. So it's the Quantum Computing Society of the Philippines. I'm sure you guys are familiar with the idea of a qubit, right? So you have some system. It could be an atom. It could be the nuclear spin states of the atom. It could be the electronic levels of an ion, or it could be the spin up, spin down of an electron, or it could be the lowest two levels of a quantum harmonic oscillator, which is created by a superconducting LC circuit. So there are many different implementations of qubits, but something that is common to all of them is that they're often unreliable. Unreliable meaning maybe the control of the qubit is not precise. So, you try to take a qubit from 0 to 1, but the pulses or the sort of electromagnetic waves that you use to manipulate that qubit are not perfectly calibrated, and so it doesn't that transition from 0 to 1 doesn't happen perfectly. Or maybe if you're using an ion or an atom as a qubit, maybe the atom gets lost and you don't know where it goes. Okay, so you've lost your information. Um, or it could be just basic quantum fluctuations in the background in the vacuum that can cause stray or there's stray heat that affects your qubit that causes your quantum harmonic oscillator to suddenly jump from 0 to 1, or even worse, 0 to like 13, and then okay, well that's completely useless, and you've lost your information. So there's a lot of things that you can do to improve your physical qubits. So for example, if you make the qubits better, like literally if your qubit is made out of an LC circuit, a superconducting circuit, you can do better fabrication, better design. If your problem is from imprecise control, then you can do better calibration. You can upgrade your control system. But at some point, there's a limit to how much you can make these physical qubits better, and you will always need quantum error correction to make useful logical qubits out of even the best physical qubits. So how does this work? Um, for example, here's one approach. This is called the surface code. And what it is you encode your data into, let's say, 25 of these yellow data qubits, and you store the data redundantly inside these data qubits. And then you have these black qubits in between them, which are entangled. So for an example, this black qubit will be entangled with the yellow ones, the four yellow ones next to it, and it's the same for the red ones. And so these blue qubits, they will detect phase flips. So that's if your 0 + 1 qubit becomes a 0 - 1 qubit. So that's what the blue qubits will detect. But uh, the red ones detect bit flips. So that's if your zero state becomes a one state or one state becomes a zero state. So that's what this red qubits will detect. Another way to think about it is if the environment, if some error mechanism, right, performs an undesired Z operation on your qubit, then the blue ones will detect it. And if an undesired X operation is performed, then the red ones will detect it. And so the idea, basically, let's say there's a undesired X operation that has occurred on one of your data qubits. Then when you measure the black ones, you will see, oh, okay, well, I expected the black to be 0, but then now it's 1. So probably there was an X error there. If there were two X errors, then then let's say this red one will be flipped once, this red one will be flipped once, this red one will be flipped twice. So you don't observe it. But of course, in quantum, you cannot directly observe your quantum state without destroying it, and that's why we only measure about half of the qubits at a time, and we try to infer what happened, right? So when we measure, we only see, okay, so there's this one, this black one that lit up, this other black one that lit up, and now I have to guess where did the errors occur, on which of these yellow qubits did the errors occur, and also does it matter for my logical system. So here's an example uh, of how this works, say, on neutral atom qubits. So these qubits are made in the United States by a group at Harvard uh, and in collaboration with a company called Quera, or Quera, Quera, Quantum Era, I guess. And so they have something like 450 neutral atoms arranged in an array like this. So every dot that you see is a site for an atom that you can use as a qubit. And within this sort of giant sort of rectangle full of atoms, they have different zones for where the atoms are then responsible for different things. So, for example, um, you might have some atoms here, up here in the storage zone, and you would use lasers to move a whole block of them down into the entangling zone. You move qubits next to each other, and when they're next to each other, you can shine another laser on them to entangle them, and then you can move them away into, say, the readout zone, where you shine a third laser onto the atoms, and basically, if that allows you to do some measurement. Either you can detect that it's 0, or you detect that it's 1, or you detect that actually I lost the atom, I don't know where it went. So and so you could do all sorts of cool things like that. So if you guys want to read this paper and see how a real quantum computer works today, or I suppose in as of June last year, this is a fantastic read. I really love this paper. Um, and so they implemented the surface code. So this, as in this code that I showed you earlier, they tried to implement this. And here's what they did. So they tried to do a D3 and a D5 surface code. So this is a small surface code, and a slightly larger surface code. And what you expect is that when you use a bigger surface code, that is, when you have more redundancy, the error rate should be lower. And so this is what they observed. This is a big result, in fact. So you see that the logical error for a small surface code, and then it goes down when you increase the size of the surface code. And then you can also do things like you can compare decoders, like how do you tell what is the algorithm that you use to try to infer the error? They tried to do that. So they used this most likely error decoder. They also used an AI decoder. And they also tried to be aware of, say, atom loss. So this is the phenomenon where you use an atom as a qubit, but then it disappears. Okay, now that it's disappeared, can I still preserve my quantum information? So that's what they were able to do. And then another thing that they were able to do is to do logical operations, right? So you can see here in the top panels, these are two surface code patches each. So you have 25 qubits on the left, 25 qubits on the right, and it's the same for this other scheme. And in one scheme, you try to move the qubits next to each other. You do the entangling, and then you're done. Whereas in the second scheme, you keep the qubits where they are, but then you add more qubits to do the operation, and then you take them away. So, so people are now experimenting with like sort of different ways of doing essentially C naught gates between logical qubits. Uh, Now this quickly becomes a more complicated thing to do once you have more and more qubits. So of course, more qubits, more power, more great, but also more qubits, more problems. Like if your quantum error decoding problem becomes like this, then it becomes harder and harder to quickly and accurately correct your errors. And in fact, if you try to go through time, then it becomes a sort of 3D graph, which becomes really, really difficult. And so, um, if and even if you have a different system, so this is a trapped ion system by the company called the Quantinium, and what they have is they have a this long racetrack along which they can trap ions. They can store ions in this ring. They have a junction here where ions can cross over to any one of the four sort of paths. And then they have these gate zones where you can do 1 qubit gates or cooling or 2 qubit gates or even state preparation and measurement. That's all done in these 8 zones where they say quantum logic. And if you have an architecture like this, then do you still do the surface code, or is there a different way that you can entangle your qubits to protect them? And how do you do operations? These are really, really big questions, and the industry is like super active, and there's a lot of work still to be done to make a useful quantum computer. Um, and so just to summarize this little bit, right, quantum error correction is really a complex, massive real-time data processing problem because once you've decided how do you entangle your qubits, how do you do operations on them, then you need to think about, okay, how do I interpret this fast enough so that my quantum computer is actually useful, right? Because if I if I look at this graph and I try to decode it by hand, yeah, sure, that would be a really fun pen and paper exercise. But for a useful computer, maybe you want to do this kind of detection once every microsecond, and how do you design algorithms, hardware, software, whatever you need in order to do this cycle of collect the error, decode the error, correct the error, and then and so on and so on. How do you do this um, with fast enough and accurate enough? So in our estimations at Riverlane, you process something like 100 terabytes per second, right? This is the entire Netflix's data rate just for a single computer. You need to process it inside the same room. And also it has to be fast. You have to be able to return the results within microseconds. So how do you do that? It's a big deal. For us, we believe that the only way to keep up with this is to build dedicated quantum error correction chips. This is our business idea. This is our technology idea. And we'll see if it works out. Of course, we're building the right solutions. We try to build the right solutions for the right computers, but this is kind of our vision. And then maybe finally about what I actually do now. So all of this that I spoke about, the quantum error correction, is the really fun, the theory and the engineering and the experiment bit. Um, but as I said before, I had already been a researcher. I'd done my research career at CERN. And then at CERN also started my engineering career, and I continued my engineering career as I moved into quantum computing. But then, about a few years ago, I felt that I really wanted something that was more around people, something that helped me get exposure to the business, and in some way, like I am also quite fascinated by economics and how the world works in that way. And I found product management for me to be some way of still using my science experience, still using my engineering experience, but being able to sort of learn how to lead, to learn how to do business, to learn how to, in a way, use capitalism for the benefit of this really cool science project and this really cool engineering project that is quantum computing. And so I offer this to you not just because this is my story, but maybe also as an encouragement that just let's say if you're doing physics now or you're doing computers now, it doesn't necessarily mean that you have to be a physicist. It doesn't necessarily mean you have to be an engineer or software engineer, right? It's possible to move away into a slightly different career. It's possible to still use the things that you've learned and develop the talents that you guys are developing now. Um, and for me, it was also very fortunate because, when um, uh, oftentimes I pray for a new job because maybe I want something different, or maybe I'm a little frustrated with the problems that I have at work. And then it turns out that I didn't have to go anywhere. The job changed from under me to something that I actually, wanted and enjoyed. And so this is something that I'm very, very grateful for. So I offer this to you as a sort of maybe a little bit of hope of and to broaden your horizons. Again, you're in physics or you're in computing, that's awesome. Um, and it doesn't mean that you have to stay there, right? If you want to stay there, cool. But if you find that there's an opportunity where you could learn something, but maybe risk leaving behind, what you had before, I mean, I still get to do the science. I still get to do the engineering, but I do it vicariously. I do it now through other people, and I enable other people to do it. And it brings me so much joy. So that's me on my career and product management and quantum computing. What's next? Who knows? I'm still here and I'm still really enjoying this thing, and um I'm very open to what the future brings. So thanks everyone for listening to my little chat, and happy to take questions.
Okay, thank you so much, Dr. Gabriel Gallardo. So if you have any questions, please do send them via the Zoom chat.
Oh, someone's raising their hand.
Oh, okay. So Vincent, you can unmute.
Hi, good afternoon. You hear me?
Yep.
Yes.
Thank you. Okay, been a long time that um I am watching your series of webinars because here in the Philippines, the quantum ecosystem is still new, and
Mm.
I understand that you guys are trying to become mainstream sooner or later. So,
Mm.
with this topic now, it caught my attention because he mentioned about the CERN, and
Mm,
in light with, I mean, recently we knew that U.S. renewed um, moon missions, the one
mm,
they did in the 60s and 70s. And
mm,
also, we can't deny that the if you are familiar with the rocket propulsion technology, in my opinion, it's one of the most stubborn technology to develop. And almost like 2 centuries passed, and we're still stuck with like the firecracker system. You blow up the fuel, and it will propel you to destination beyond the earth. So in your opinion, how do you think quantum technology soon will revolutionize rocket propulsion technology? So, for instance, I mean, so in the distant future, probably after like hundreds of years, we can finally propel to the stars. Because, in my opinion, Mars could be the last frontier. And after that, nothing beyond it. You need to go to the other stars. So, how can quantum computer change that technology? Thank you.
mm. That's a good question. So normally in quantum computing, we there's not that much discourse that I'm aware of that is revolving around rockets. So we think a lot about quantum simulation. We think about, for example, like material science, like how do you develop good fertilizers that improve nitrogen fixation in the soil, that doesn't hurt the environment, or how do you improve this thing and that thing, like sort of very concrete, literally down to earth kinds of problems. My understanding of rockets is that they're not limited in that way that you think in terms of the propulsion. Because ultimately the best thing that you can do for a rocket is Newton's third law. You expel some, you expel as much mass as you can at as high a speed as you can, and then that momentum difference propels you forward. You can plot your course to take advantage of like the proximity of, say, Mars, um, and and add energy to yourself and remove energy from yourself as appropriate to reach your destination. But it's not my impression that we're limited by the fuel. Certainly by maybe if you could improve on the energy density of the fuel, you can carry less and go further. But it's my understanding that it's really the astronomical distances, no pun intended, but the really astronomical distances required to cover in space travel, that is the limiting factor, and not anything that we can optimize computationally.
Great. Thank you, Dr. Gallardo, for your answer, and also Vincent for your question. Actually, our next speaker later will be someone who actually has experience in space engineering. So maybe Vincent can also ask the same question again later. But yeah, so we have another question actually in the Zoom chat. So the
Mm.
question is, given your experience working across quantum computing, particle physics at Atlas and CERN, and product management, what do you see as the biggest challenge in translating complex quantum or physics research into practical, scalable technologies that non-experts can understand and adopt?
Yeah, this is a good question. Admittedly, my career, as you have seen, has been very much in the field of not practical, not scalable technology that experts really enjoy. And there's motivation definitely for, understanding and adoption of the public. Like, particle physics and how the world works is always very captivating. Um, but when we do these things as physicists, at least in particle physics, when we do these things, we don't really have an eye on like practical applications. It's fundamental science, and fundamental science is important to do just because it's interesting, like people are always curious about the world, and we get to do it, and that's really good. And it's somebody else's job, how to say, to translate these things into something practical. So now in quantum computing, this is a little bit more practical, right? So some people are definitely just in it for the math or just in it for the physics. But for me, um, how we translate this into something sort of usable and scalable is still quite difficult because the applications for quantum computing are still so far away in terms of like how many qubits do you need and how good do the qubits need to be for good quantum computing is still years away, 5 years, 10 years, maybe 15 years away, depending on who you believe. And so just doing the work to build test systems is very hard, and doing the work to try to come up with use cases and to make those use cases accessible sooner is also very hard. Um, so you asked me what the biggest challenge is, and I can't really say which one is the biggest really, but it's all very challenging.
Yeah, there's probably so many challenges in doing that.
Mm.
But yeah, thank you for that. And then we have another question in the chat. Um, they're asking if it's possible to detect heartbeats with quantum computing as claimed by the US government, also known as ghost murmurs. I'm not familiar
I'm
with
not I'm not sure I understand the question, but you may know that you can detect your own heartbeat simply by putting your ear to your chest or having, your mom to do this for you. We also have very advanced medical devices that can detect the pulses sent by your brain to your heart, and you can detect the response of the heart as well. Um, Again, this is not something that the quantum computing community is focused on at the moment, as I understand.
Yeah, if ever, maybe you can ask a follow-up question, J. Carl, if you have. Uh, it's more on the quantum sensing side using NV centers, says Javas.
Okay, yeah. Okay, so that's out of my field. Quantum sensing
Mm,
is not really what I think
yeah.
about. Thank you, Javis.
Okay. The next from Iana, we have a question. In rocket making, what would be a good secondary mission that incorporates quantum computing in a way? Again, for rocket topics, maybe we can address it to our next speaker later.
Mm.
But if you have anything to say, Dr. Gallardo, that would also be
Well,
great.
there was an idea that maybe you can do quantum computing in space because space is cold. And certain kinds of quantum computing need a cold environment. But it's a fun idea to think about until you think about how do I get the quantum computer up to space, which takes a lot of energy. And once you've done that, then any energy savings that you have on the cooling is immediately lost because of the stuff you have to send, because you have to use the rocket.
Okay, great. And then something that's I think more related to your field, sir,
Mm.
is how close are we to achieving logical qubits with error rates below physical qubits?
Yeah, this is a
Error.
good question. So this has been demonstrated over the last 3 years. So the first demonstration was by Google. So on their superconducting system, they managed to create a logical qubit out of 17, 49, and even 97 physical qubits, all with the error rates that they have. And they demonstrated that the larger you can make the logical qubit, the more error protection that it has. And other companies and groups have followed up with similar experiments. So Quantinuum, as I mentioned before, they have their own quantum error correction things, and also Harvard Quera. So for me, these are the three biggest demonstrations of quantum error correction.
Okay, great.
Yeah.
Um, Then next we have two questions from PPL. I'm sorry if I botched
Yep.
the pronunciation of your name. But first is, what is the difference between bit flips and phase flips? And what components do we observe to understand what types we are observing?
Yeah. Okay. So that question is, so bit flip is when you have essentially an unwanted Z operation on a physical qubit, right? So that takes the 0 to the 1. Sorry, that's an X operation. And a phase flip is when you have an unwanted Z operation. So that takes like the plus state to the minus state or the minus state to the plus state. And so the clever way that you entangle the data qubits with the ancillary qubits lets you observe which one is the one that happened. Yeah.
Okay.
And then there's a second question which I can read. We're only measuring half the qubits, otherwise the state will collapse. So how can we guarantee that we get the full picture when we only measure half of it? And the answer to this is that we cannot guarantee this, right? You can only say that the most likely error is this one. And this is a limitation of quantum computing, because in classical computing, you can always make a perfect copy of your data. You can make as many perfect copies as you want, and then you can always compare, right? But in quantum computing, you have the no cloning theorem, which means you cannot make copies. You can only teleport information from one place to another. And with this limitation, you have to accept that you can only probabilistically guess what happened to your error, well, how it happened to your qubit. Yeah.
Okay, great. And then Chris Pulo is asking, what's the latest news about quantum computers? Maybe instead of latest week, any interesting latest news for you, Dr. Gallardo?
Yeah, for me, so I focus a lot on, this is related to the next question, the differences on error correction on fast and slow qubit type. So I focus on error correction for slow qubits. And for me, the most exciting news I already shared with you, which is the Harvard Quera paper and also the Quantinium paper. These are the most exciting ones so far.
And to answer the next question on the differences.
All right, differences in fast error correction and slow error correction. So for fast error correction, you need to return results within microseconds, which is incredibly hard given the amount of data that you need to process. But on slow qubit types, you tend to have qubits that are more flexible. So like you can easily entangle them in different schemes. And so for them, the problem is about what's the best scheme that I can do that minimizes my overall computing time while preserving my logical fidelity.
All right. Okay. And then for the next question, someone's saying that they like your ring. Um, uh, can we make images like that in quantum computer in the atomic level? What images would
So
this ring?
this is a ring. This is Aragorn's ring from the Lord of the Rings.
Oh,
Um, and with quantum computers, so Quera, they often have this fun demonstration where they just place atoms where they want in their lattice to make whatever images that they want. So they often close out their slides with a picture of their atoms spelling thank you, and as you like. Anyway, I have to go now. So
okay.
thank you so much
Thank you so much,
for having
Dr.
me.
Gallardo. We'll just do the presentation of your certificate. So,
Okay,
um,
good.
we present this. This certificate acknowledges that Dr. Gabriel Gallardo has masterfully shared insights as a speaker in World Quantum Week Spotlight Talk, a webinar in celebration of World Quantum Day signed by Engineer Ethel Ong Badyang and Sir Bobby Corpus Jr. So thank you so much, Dr. Gabriel. And maybe we can take a picture. So can we have our logistics to take a picture with Dr. Gabriel? Okay. Then,
Yep.
all right,
I'll take the
Chavez.
photo. In 1, 2, 3, smile. Right, once more. 1, 2, 3, smile. Thanks so much.
Okay, so for
Outstanding.
any questions, maybe you can send it to our QCSP team and we'll try to forward it to Dr. Gallardo. So for any other follow-up question. So thank you so much, Dr. Gallardo, and we hope you have a good rest of your day. Thank you.
It's good to be here. Enjoy the week. Bye.
Thank you so much. And for our participants, please answer the following evaluation form for our Spotlight Talk number 1. Okay. So, okay, let's just wait a few seconds and then maybe we can send the questions, the form as well through the Zoom chat if someone could send it. What time is the second session? So it should start actually at 5. So maybe we'll start by 5:05. Once you have had the time to answer our question. So our survey. So here is the post survey form. Even sent it through the Zoom chat. So we'll be having the second talk in the same Zoom room. So please don't leave. And since a while ago there were some questions regarding space engineering. So our next speaker actually has some experience in that field. So you can still prepare your questions for him later.